All right, 18.11 is titled Nucleophilic Addition. So now we're going to start looking at nucleophiles attacking the carbonyl. Again, this is a mechanism we've seen many times. Imagine this is a Grignard. It attacks your carbonyl, kicks your pi bonds up to your oxygen, gives you the negative charge. All right, which then you could protonate it with something acid or something of some sort. So basically, it's grabbing that to give you an alcohol. In this case, we're forming an alcohol. Most cases, you do form an alcohol. Okay, so a strong nucleophile attacks the carbonyl, forming alkoxide ion, which is then protonated. Oh, sorry. Aldehydes are more reactive than ketones. Why do you think an aldehyde is more reactive than a ketone? All right, well, if you think about it, aldehydes are less sterically hindered. It has nothing to do with electronics. Electronically, they're pretty much the same. It's just that aldehydes are less sterically hindered. So these type of nucleophilic attack additions work best with least substituted compounds, like we saw in the SN1, SN2 case. Primaries react faster than secondaries, and so forth and so on. So aldehydes and ketones do the same thing. Okay, the Wittig reaction. This is pronounced Wittig, not Wittig. So W is with a V. Wittig won a Nobel Prize, I think back in the 60s. This is a very important reaction. Notice it's a carbon-carbon bond formation. You're forming a carbon-carbon bond. Not only that, you're forming a double bond. Basically, you're starting with a carbonyl. This oxygen gets substituted for whatever carbon group you have attached to this phosphorus. These are phenyl rings. Okay, that's kind of the shorthand for an aromatic ring. So it's triphenylphosphine. We're going to learn how to make this complex, and we're going to learn the mechanism of this reaction. But basically, whatever carbon group you have attached to your what's called a phosphorus ylid, that's pronounced an ylid, not yillid, ylid. Whatever is attached to the phosphorus, that's what replaces your oxygen, okay, to form an alkene. So you're forming an alkene in this reaction. It's kind of a really neat reaction. So it converts a carbonyl to a double-double bond, and the phosphorus ylid is the nucleophile. Okay, so let's first talk about how you prepare the phosphorus ylid. Triphenylphosphine, okay, remember this is a phosphorus with 3 aromatic rings around it. That's what this is. It's a pretty big group. Okay, it does a standard SN2 mechanism on an alkyl halide. Usually primaries are what you want. You need a primary or a secondary. Okay, you cannot do tertiary. The reason is because you need a hydrogen to pluck off to form a negative charge. Okay, so you have to have at least a primary. I guess, well, it's hard. It's not really. Yeah, I guess it's a primary alkyl halide versus or a secondary. So this could also be in our group, but you have to have at least one hydrogen. Okay, but SN2 reaction to form a phosphonium salt. Okay, phosphonium salt. It's a phosphorus. It's charged, so it's a salt. You then use butyl lithium. The butyl lithium is just a strong base. You're basically quenching the butyl lithium to pluck off this hydrogen right here. That hydrogen is slightly acidic. Okay, it's more acidic than a typical carbon hydrogen because you have this plus charged phosphorus next to it. So you kind of have a conjugation that's actually occurring here, where you have you have a pi bond here with a plus charge, and these electrons, hyperconjugation, and these electrons are already being hyperconjugated into there. So this hydrogen is very, very partial positive. So if you had any type of strong base into here, it is going to pluck off that hydrogen and form a negative charge on your carbon. All right, now this negative charge can form a double bond. This is kind of a resin structure. This is actually the major resin structure because it has no charges. Okay, so this is kind of the major resin structure, but you can think of it as a carbon negative that's stabilized by a phosphorus. Okay, so this is how you prepare the phospholipid. Okay, so it's just to kind of remind you, the phosphorus does an SN2 reaction on your whatever group you want to attach onto your carbonyl. That's the group you have. Okay, like I said, it needs to be primary or secondary. It can't be tertiary because you need a hydrogen. If you have 3 R groups here, all right, what hydrogen is it going to pluck off? It can't pluck anything off. So that's why you can't have a tertiary. You got to have primary or secondary. Okay, so prepared by triphenylphosphine and an unhindered alkyl halide. Butyl lithium then extracts a hydrogen from the carbon attached to the phosphorus. Okay, once you've formed the ylid, Okay, here's my ylid. Once I form it, it just attacks the carbonyl and kicks up the pi bond to give you this compound. Okay, and purposely putting this oxygen next to this phosphorus. Okay, because what's going to happen now, you form this compound, what happens now, you notice you have this phosphorus. Phosphorus is pretty big with a plus charge. So these electrons attached to the oxygen are going to bond to this phosphorus, okay, and form an oxaphosphatane. Say that. That's a fun word to say, oxaphosphatane. All right, kind of cool. Kind of this four-membered ring compound that with a phosphorus there, an oxaphosphatane. Say it fast, it's really fun. Okay, so form this oxaphosphatane, and what eventually is going to happen is this is going to collapse down. These electrons are going to go to here, and then these electrons are going to come down here, okay, to form your double bond, and then to form a double bond phosphorus oxygen bond. Let's see in the next slide. So there you can see in the next slide that these electrons right here are, oops, sorry. These electrons right here, right, are flipping down to form your pi bond, and then these electrons are flipping up here to form your pi bond here. So this is going to be one molecule, and then this is going to be the other molecule where you basically transferred a double bond to. So here's your double bond. This is a very stable compound, this triphenylphosphine oxide. Okay, incredibly stable. So the driving force is to make this incredibly stable product. It's so stable you can't do anything with it. You can't even break it apart. All right, there's a lot of waste in this reaction. That's one of the downfalls, but it is an extremely good reaction. Okay, so the oxaphosphatane will collapse, forming an alkene and a molecule triphenylphosphine oxide. All right, so here's kind of some hints. The publisher does this. I kind of like them. If you plan a Wittig synthesis, do it with the less hindered end of the double bond coming from the ylid. So if you have a double bond, whichever end is less hindered, that should be your ylid, because you want to have the least substituted, because that's doing the attacking. Okay, because remember you have to do an SN2 reaction on it to begin with. All right. So here they kind of show you a compound, and they kind of want you to do a Wittig on it. So why don't you do that for homework, and we can talk about it in class when we get together. Okay, let's talk about some more of these reactions. This is the hydration that I was talking about, where you can hydrate carbonyls, and this happens all the time. This is actually in equilibrium. All right. Like I said, ketones and aldehydes have a little bit of water in them. They're very hygroscopic. They pull water out of the air, and they form what's called these hydrates. It's called a geminal diol. Geminal meaning it's on the same carbon. So your diol, your two alcohols, are on the same carbon. Okay. So with a little bit of water, this can actually form, and it does form. Okay, so in aqueous solutions, a ketone or an aldehyde is in equilibrium with its hydrate, which is called a geminal diol. With ketones, the equilibrium favors the unhydrated. So this is the major form. Even in aldehydes, this is the major form. Okay, so here's the mechanism. You usually also need a little bit of acid in there, just a tiny bit. So anytime you have acid, obviously the first step is these attack to protonate your oxygen, makes your carbon much more partial positive. The lone pairs from your water attacks, kicks up your pi bond to form this intermediate, which another water molecule comes by and plucks it off. That's why this is acid catalyzed. You're reforming your acid right there to form your geminal diol, or your hydrate. Okay, very straightforward. Okay, this is base catalyzed, same type of thing, except you don't protonate first, you have the hydroxide added. Okay, so what's so exciting about that? Well, because of that, they've come up with a bunch of reactions that can be useful. This is called a cyanohydrin, same exact thing, but rather than having water attacking or a hydroxide attacking, you're having cyanide attack. Okay, now this is not a reaction I would like to do, because this is hydrogen cyanide, which has been used in the gas chamber. Okay, it smells like almonds. If you ever smell almonds, that means you are near cyanide and you need to get away. All right, unless you are actually in the presence of almonds, then don't worry about it. Anyways, your cyanide attacks the carbonyl, kicks up your pi bond. This then protonates, and you get what's called a cyanohydrin. Cyanohydrin. That's the hydrin part of it. Okay. HCN is highly toxic. But anyways, that's the cyanohydrin. This is an imine. This is how you form imines. Okay, we're going to look at the mechanism here, but the imine, same type of thing. You protonate, and then your nitrogen starts attacking. Okay, so there's different type of nitrogen analogs that you can use, but let's look at the mechanism. A lot of these mechanisms, you can notice, are very similar. What's the first thing it does? Protonates, okay, forming this very partial positive carbon. So again, in this book they like to show this resonance structure to kind of show you that this carbon is very partial positive. So your nitrogen is going to attack that carbon. All right, you then pluck off the hydrogen. That's the reformation of your acid. Those electrons go back to the nitrogen to form this compound, okay, which is an alcohol, all right, an amine. All right, so your alcohol then reprotonates to form a water molecule, which can easily leave. What actually drives this is these lone pairs actually pop down to kick out your alcohol to actually form this compound. That's why, again, I don't like this structure that your book keeps doing. If you want to know it, that's fine. But what actually happens is these lone pairs pop down to kick out your water to form this protonated imine, which then water comes by, deprotonates to reform your acid to form your imine. Okay, imines are very useful. This just tells you some hints about the mechanism. It's an acid catalyzed followed by a dehydration. All right, and these are just some examples of the nitrogens. You have to have a primary amine. It's got to be primary because you need the two hydrogens. You need two hydrogens to combine with the oxygen here to form a water molecule. If you don't have two hydrogens, you can't form this. So that's the other thing. You need a primary amine. Okay, so here are some examples. You have ammonia. You can have whatever carbon group you want right here. A hydroxylamine. Those are kind of interesting. Hydrazine. We're going to talk about this. This is used in a reaction called a Wolff-Kishner reaction. Wolff-Kishner. We're going to see this later on in this chapter, where you form this hydrazone. Phenylhydrazone, which has a phenyl ring, and the semicarbazone. Not things you got to know, but just know you can make several different type of imines. Okay, we're going to stop there and pick it up on the next video.